Hello everybody, welcome back to Calculus. Today we are looking at section 6.4 actually, not 6.3, so I just need to make a small little adjustment right here to make it a 4. This is going to be a section on, once again, physics. This is, I think, the third installment of this section. In the past, we looked at, I think it was Hooke's law, and then afterwards we looked at dragging or pushing something up and down, basically pulling ropes, so then that way you can figure out how much work is going to be done. Now we're going to be looking at work pumping out liquid from, say, some sort of trough or some sort of cylindrical, I guess, like container. So here, the problem is going to be the following then, okay? I want to find out what is the work that it's going to take to pump all the water through the top of the cylindrical tank on the right-hand side. So you can see the illustration over here. We have a cylindrical tank where the radius, the top over here, is going to be 4 feet, and then the height is going to be 10 feet. And what I would like to do is take all the water and just pump it upward like this then. Okay, what I'm going to give you also is the density of water because that is required for me to figure this out. So let's go ahead and begin. So first of all, what we'll do is, just like all the calculus problems that we've been doing so far, we're going to look at a small little cross section and then figure out what's going to happen from there. So here is going to be my slab that I'm going to focus on. And for the slab, it is circular. And in addition to that, there is a small little thickness, which is going to be vertical. So if it helps you, maybe what I can do also is I can apply the XY axes on here so you can see where we're going to get our variables from. Here we have the X, here we have the Y, and where the slab is going to touch the curve or touch the line in this case, let's go ahead and call it X comma Y then. So according to this picture, my volume of that slab that I want to focus on, the area, actually the volume, I'm sorry, is going to be equal to pi x squared multiplied by delta y, because pi r squared, that's the circle, and then multiplied by the thickness, that is going to be delta y, because once again, it is vertical. Now, what I would like to do is I would like to take that slab and pump it up to the top, okay? So we're going to go ahead and look at that in just a little bit. But first, what we need to do is let's go ahead and fill in a few more things. For this slab that I just found out, the unit for it is supposed to be cubic feet because, well, feet is basically what we're using in this case. What I need to do now is take that slab and find out what is the force. Okay, I need to find out what is the force. And that's where the density comes in, because the force of the slab is going to be equal to the density, which in this case is 62.5 pounds per cubic feet, multiplied by the volume of the slab, so you can see how the cubic feet cancels out. So let's write it out, 62.5, and then cubic pounds per cubic feet, multiplied by, as we said, pi x squared delta y, and then that's going to be cubic feet also. So note how, once again, as we said, the cubic feet will cancel out. So everything now is in terms of pound, which is what we want. So just to clean this up a little bit, 62.5 pi, and then we have x squared delta y, and then this is going to be, again, not cubic feet. It is going to be pounds then. Okay, so, oops, made a small little adjustment, but we can fix it. So let's see, that is pi x squared. Okay, so then that means that what we have right here is delta y, and then this is going to be in pounds. All right, now that we have the force of the slab, if you remember, it's supposed to be work is equal to force times distance. So I need to figure out what is the distance that that slab will have to travel. Now, unlike the previous problems where you're only going to travel a small little increment, you're not going to do that, because what we're going to do is we're going to take that entire slab and travel it all the way up to the top, because we're just going to assume that, that slab, when you pump it up, it's not going to change its dimensions at all whatsoever. All of these slabs, when you pump it up, it's always going to be the same, no matter where it goes. Okay. And besides, the other thing that tells me that we're not going to pump it up by a little bit is that we already have a delta y in there. So we don't need another delta y in there. That's going to be kind of strange. But anyhow, the distance that that slab will have to travel is going to be this piece right here vertically. Well, looking at my picture, if you remember, y is supposed to be the vertical distance from the x-axis to that slab. 10 is going to be the entire distance vertically. So then that means the piece that I'm looking for, if this is y right here, and if the whole thing is going to be 10, then that means the distance it has to travel is 10 minus y. So that is what I'm going to put over here. The unit for that one is going to be in terms of feet. Looking at my force, looking at my distance, if I multiply those two together, we're going to go ahead and get our foot-pound, which will give us the work that we need. So the work for the slab is going to be equal to 62.5 pi x squared multiplied by 10 minus y, and then we also have delta y. If I want to find out what is the total work, then that means that it's going to be the sum of every single one of those slabs then. So summation of 62.5 pi x squared multiplied by 10 minus y, delta y, and that's where our integral is going to come from. The integral, let's see, 62.5 pi, once again, we have x squared, and then 10 minus y, and then dy. My boundary, vertically, all my slabs are going to be from very bottom all the way to the very top. So that means it's going to be from 0 to 10. Now, just like all the other problems that we've been doing so far, I have two variables. I have x and I have y. I have dy. So that means I need to get rid of this guy right here, x. So basically solve for in terms of y. And that's where, again, we're going to have to look at the two-dimension aspect of this, because then we can figure out what's the relationship between the two. Now, drawing it on the bottom so you can see it a little bit better without all that extra stuff. Here is that line, which is going to be the side of the cylinder. The coordinate that it goes through is 0, 0. The coordinate that it goes through on the top looks like it's going to be 4, 10, because you have the radius of 4 and the height of 10. Well, that is definitely going to be a linear equation. Y is equal to, the slope in this case is going to be 10 over 4, which can be reduced to 5 over 2x. And the y-intercept is going to be 0. So there's my relationship. So what I'll do is I'm going to go ahead and make that substitution over here. X is equal to 2/5 of y. So as my final substitution from 0 to 10, 62.5 pi, and then multiply by, looks like it's going to be 4/5 y squared multiplied by 10 minus y dy. And so if you solve for this integral, the numerical value of it using FTC number 2, and the method probably using like a power rule or something like that. Or if you want, you can use finite integration, but probably better if you do it by hand. That will tell me the total work that it's going to take to pump all the water out of this tank then. Okay. All right, let's look at another problem very similar to this one. This time around, here is going to be my setup then. A semicircular trough filled with Mr. Chan's crab juice. It is drained from the bottom and then funneled out through a vertical pipe that is 8 meters long. The radius of the trough is 5 meters, while its width is supposed to be 10 meters. How much work would be required to suck Mr. Chan's crab juice out of the trough? So over there on the right-hand side, you can see the picture of that trough. And then there is a funnel, which is in purple, where you can see that the crab juice is going to be able to enter and then get sucked out from the bottom all the way to the top, which is 8 meters long. The radius of that semicircle is supposed to be 5 meters. And then also the width is supposed to be 10 meters. Now, I'm not really good at like these units, so probably 5 meter is a lot, and 10 meters a lot, and 8 meters a lot, but that's why I teach math and I don't teach physics. So anyhow, I want to find the work that it takes to pump all of this out of the trough then. So first, just like before, what we'll do is we'll go ahead and set this on the XY coordinate, so then that way we can see some variables. In 2-dimension, what I'm seeing is that we have a semicircle that I have to consider, okay? And then for the semicircle, the equation of it is supposed to be x squared plus y squared is equal to 25. Technically, it's just the upper half, but we can modify that equation in just a little bit. So here's x, here's y. And just like before, what we'll do is in that trough, we're going to go ahead and look at an instantaneous moment where you have the slab. So that right there in the picture above is basically located over here. So we're going to look at a slab right here, okay? And I want to see where the slab is going to be traveling and what's the weight of it and what distance it has to travel and all that stuff, just like before. All right. So where it touches the curve, again, we'll go ahead and call it x comma y so we can get the relationship between the two. So first item, oh, by the way, the density of the crab juice, which again I have to give you, is going to be 2,000 kilograms per cubic meter. And again, I don't know if that's a lot, but yeah, 2,000 just sounds like a good number. Okay, so first, what we'll do is we'll solve for the volume of the slab. Okay, it's the volume of the slab. Since all of these slabs are stacked vertically, then that means I know the thickness is going to be delta y. Now, the dimensions, the area, that is going to be this piece over here horizontally. Well, half of it is supposed to be x, so that means that it must be 2x. Then you also have to multiply by how far it stretches out to. So that's where the 10 is going to come in because it's supposed to be 10 meters then. Okay, so this right here is kind of like the length. This right here is the width, and this right here is the height. The volume of that, let's see, it is going to be in terms of cubic meters because those are the units in this case. Now, we're going to go ahead and clean that up a little bit. So that's going to give us 20x delta y, and then this is in cubic meters. From there, we're going to use, again, the density in order to figure out what is the force of that slab then. Okay, so I'm going to go ahead and multiply by the density. So this right here, be very careful. Again, we're not in America, so that means that we're going to have to deal with mass and hence multiply by gravity for acceleration. So we need to do kind of like an intermediate step. If I want to solve for the mass of the slab, okay, M for mass, and this is not how you spell slab. Slab is like this. That is going to be 2,000 kilograms per cubic meters, and then multiply that by 20x dy or delta y, and then that's in terms of meters. So you can see how the meters are going to cancel out, leaving you with kilogram, and that's going to be our mass then. So let's see, that's going to be 40000. I think that's how many zeros we have. Yeah. Then we have x, and then we have delta y, and then that is in terms of kilogram. If I know the mass of the slab, in order to get the force of the slab, then that's where we're going to now multiply by the acceleration, which is the gravity. So that's 9.8 meters per second squared, okay? Multiply by the 40,000 x delta y, and then that is going to be in terms of kilogram. All of those units, just to simplify, that's gonna come out to be Newton meters. Sorry, it's going to be newtons. So we'll just go ahead and write that then for short. So 9.8 multiplied by 40,000. I'm not going to multiply that out because, well, I don't have a calculator on me. I technically do, but I'm just getting kind of lazy. So anyhow, that's going to be in newtons. We have the force. Now let's go ahead and consider the distance that it's going to have to travel. Okay, so the distance that the slab has to travel. Well, in the picture, right, remember what it says in the prompt actually. It says it is drained from the bottom and then funneled out through a vertical pipe that is supposed to be 8 meters long. So what that means is this slab has to go to the bottom and then afterwards come up all the way by 8 meters. Well, the distance over there, remember vertically, is supposed to be y from the slab going to the x-axis. So then the distance is going to be y plus 8. So that is going to be my total distance traveled then. So 8 plus y, and that is going to be in terms of meters. We have newtons, we have meters. So newtons meters, that's going to give us the joules because once again, work is equal to force times distance. So put it all together. The work of the slab is going to be equal to 9.8 multiplied by 40,000 multiplied by x multiplied by 8 plus y, and then we have delta y. And that right there is supposed to be in joules, right? Because that is supposed to be newtons meter. Let's see, total work of the slab, the total work of all of them put together. And let me just draw my W a little bit better. So the total work is equal to the summation of everything that we just said. So that's where our integral is going to come in. So 9.8 multiplied by 40,000 multiplied by the integral of x multiplied by 8 plus y dy. And then it's the boundary from 0 to 5 because if you remember, this is supposed to be a semicircle. where the radius is equal to 5. Now, earlier we are saying that there's a relationship between x and y, and that's where this equation of the circle comes in. So notice over here, I have an x, which I don't like, so I need to replace it. So if x squared plus y squared is equal to 25, then x is equal to the square root of 25 minus y squared. So my final setup is going to be 9.8 multiplied by 40,000 multiplied by 0 to 5 integral from 0 to 5, and then 25 minus y squared multiplied by 8 plus y dy. And so the way you would solve for this one, you probably looks like you're going to need to do a little bit of u substitution. In addition to that, using the area under the curve, solving for the area under the curve geometrically, because you have the square root of 25 minus y squared. So that tells me there's going to be some sort of pi involved in there. Okay. All right. Well, there you go. Thank you so much for watching. I will see you guys next time, and have a good one. Bye-bye.